Hey guys, it's Luke and welcome to this video on catalytic asymmetric synthesis. This time we're going to be looking at the sharpless epoxidation. So we use DET in this, which is shown there. And we also use tin, isopropyl, oxygen 4 times, something like that. And we also use tertiary, we basically use BUT, Hobbit basically. It's basically Hobbit there. I think I might have included an extra O by accident, but the negative det attacks on the top and the positive attacks on the bottom, just kind of opposite to what you would expect. And then let's say we use the negative one, both attacking from the top, so we get something that points towards us and epoxide pointing towards us. Products are useful for building blocks, so this is using one of the products we've made here, reacting it with a acid chloride. Some badly drawn arrows here, but effectively we've got that transition state there. We've got the chlorine got replaced by this H there, or O, forms a bond, and then the OMe can donate its pair of electrons onto the door bond of the oxygen, which is this oxygen here, and that can shift up to the epoxide that we've got and open the epoxide ring. Then we've got this product here, so we formed a cyclic sort of intermediate, and then we've now got a positive charge on the OMe. Add H2O to it, we can form basically a proton transfer sort of thing. We remove the methyl and add a proton onto our hydroxy group, our alcohol group, and by adding potassium hydride we can split up this diether and remove this ketone, and that gives us our alcohol product. Last few things, we've got the Jacobson epoxidation this time. This is using a catalyst. In this case we're going to use a manganese catalyst. We've got a E or cis alkene, and we're going to react that with NaOCl, and we form that product there. As you can see, this is what happens. Very straightforward mechanism. Yeah, nothing much to it. Obviously all of these are bound to the metal center. Make sure there's an oxygen coming off one of these R groups, so like for example a ring with an oxygen in it, so that can bind to the center, and that's pretty much it. That's just the curly arrows there, and that can form the epoxide in that step there. Basically we're just taking the epoxide from there and forming a bond there, a bond there. That's pretty much exactly what we're doing. So asymmetric hydrogenation, or the Niori mechanism, we've got this here, which is S-binap, and tropisomers are restricted rotation around this biaryl bond, so therefore it's chiral. Here's just a quick example. We've got an electron donating group here. We've got R-binap, which is something slightly different to that. We use ruthenium-2 as a catalyst, and all that does is effectively breaks the double bond and adds a hydrogen facing us. That's pretty much it. Amino acids synthesis is the final part here. I think there might be something extra. No, that's literally it. We can use our H1 this time, which is opposite in anti-selectivity to RH2. Sorry, that should have been rubidium up there instead of ruthenium. And we've got a donating group. We use S-binap this time, and that gives us our product, which once again just literally just breaks the double bond, and yeah, we get the product there with the hydrogen. And that's pretty much everything in this module, and yeah, hopefully it's helped. Next we're going to move on to palladium chemistry.